Good evening, everyone. Welcome to the homework portal. This is your fourth problem on homework portal. This is for IB2 students, and this will be published on 26th September, that is tomorrow. Okay, now let us begin with this. So, Ceres is a dwarf planet in the asteroid belt. Okay, before I start, this question is for 10 marks. So, I have set the timer for 10 marks, including my talk. And this question is not a question on astrophysics. The moment you start looking at dwarf planet, don't say, okay, I have not taught you astrophysics. This is a question directly on albedo, intensity, black body radiation, Wien's law, Stephen's constant, and all these things. Okay, now let us begin with this. So, Ceres is a dwarf planet in the asteroid belt. The following data are available. Okay, so you have a dwarf planet. Okay, mean distance of the Ceres from the sun. So, you have the sun here, and then mean distance. Let us say Ceres is somewhere at this point. Ceres is this point is 4.4 into 10 power 11 meters. So, this value is given to be 4.4 into 10 to the power of 11 meters. And the mean output power of the sun is 3.8 into 26 meters watts. So, 3.8 into 10 to the power of 26 watts. What does it tell you? It tells me that, okay, if other than Ceres, if any other planet is now moving in this orbit, okay, so they will all get the same type of power. Okay, no, not same type of power, same intensity. Okay, now what we'll do is let us calculate the intensity in its orbit. The intensity in its orbit, what you call it as an average intensity at any point on this circular orbit, will now be equal to P divided by 4 pi r square. Okay, so which should be 3.8 into 10 to the power of 26 divided by 4 pi into 4.4 into 10 to the power of 11, the whole square. Okay, so when I do this, let us calculate what is this value. What is that we are computing? We are computing the average intensity which is falling onto the surface due to sunlight. So, which should now be equal to 4 star 3.14 star 4.4 star 4.4. I am calculating on the denominator initially, which will be 243. So, I will write this as 3.8 into 10 to the power of 26 divided by 243 into 10 to the power of 10 power 11 whole square is 10 power 22. So, thus this should now be equal to 3.8 divided by 243 is equal to 0.0156 into 10 to the power of 26 minus 22 is 24. So, when I do this 1, 2, 3, 4, it should be equal to, sorry, 26 minus 22 is 4, I'm sorry, not 24. So, 4, which should be equal to 156 watt. So, what is this now? This is not watt, this is watt per square meter. Watt per square meter. This is the intensity received by any object which is going over here. Okay. Now, this is not what is asked. What is asked is determine the mean temperature of Ceres, assuming that it acts like a black body radiation. So, which means what? What do you mean by a black body radiator? Any intensity that you receive, you should be having a capacity to send it back also, right? Radiate it back. Okay, which means now let us find out what is the intensity received over here. Now, what is Ceres? Ceres is nothing but a planet. Now, how does a planet look like? Planet look like a sphere, right? This is a sphere over here. If it looks like a planet, what part of solar radiation, which part of the Ceres is now getting affected by the solar radiation? So, if this is the orbit over here, only this part of it is getting orbited, right? See, if I write it bigger, so this is your Ceres planet. Okay, this part of it is going to get affected. Okay, only the first half of it, only the first half hemisphere is going to get the sun rays. The next half is not going to get it at all, right? But what is our assumption? Our assumption is that whenever we have an object and it gets heated up and it radiates at a given temperature, then what do we assume? The entire body is radiating, right? We do not assume only this part is radiating, even this part is also radiating. In that case, the intensity that you receive here should be equally distributed throughout the sphere, right? Equally distributed throughout the sphere. Now, towards it, first what we will do is we will calculate what is the power it generates when it falls onto it. Okay, when it falls only on the circular path over here, because you know, if I am seeing a sphere from my angle, I will be able to see only as a circle over here, right? So, therefore, I will be able to see it as a circle and not as a sphere. I do not know, my eyes do not calculate something like the depth of it. Okay, so therefore, you just need to take the projection over here. The projection would be only a circle over here. If x is the radius of the circle, okay, x is the radius of this sphere, okay, of the sphere, then the power which is incident onto this object will now be equal to I average multiplied by pi x square. Intensity multiplied by area is power over here. So this is your P average, which should now be equal to 156 times pi into x square. I do not know what's the value of x. It's not given here. Let me just keep it like this over here. Now this is what we have. But what else is needed? See, if you want to find the temperature, which expression are you going to use? You are going to use I is equal to sigma T to the power of 4, which is the Stefan Boltzmann constant. To do this, what do you need? You need to get this value of I. What is this I? The average intensity radiated by the black body. Okay. So therefore, see, this is the average intensity due to sun, right? Due to the sun. Now I am looking at the average intensity due to the planet. What should this be? Take this P average, the power received, total power received by the planet, divided by 4 pi x square. What is 4 pi x square? Surface area of the full planet, right? So therefore, now what I will do is I will substitute this value, which is 156 pi x square divided by 4 pi x square. So pi x square cancels. So you should get 156 by 4. What is 156 by 4? Let me use my calculator. So this should now be 156 divided by 4 should be 39. So you should get the answer as 39 watt per square meter. What is this now? This is the average intensity of radiation which the dwarf planet is radiating out. Okay. Now I have got this value of I. So this is IP. Okay. So now what I am going to do is I average planet. I am going to substitute this 39 is equal to sigma T power 4, which is equal to 5.67 into 10 to the power of minus how much is it? Minus 8 sigma value into T power 4. What is T power 4? I do not know. I need to find out the value of T power 4. So when I do this, what do I get here? I will write here, okay, because I don't have much space. So I will write T power 4 is equal to 39 divided by 5.67 into 10 to the power of minus 8. This implies T is equal to 39 divided by 5.67 into 10 to the power of minus 8 whole to the power of 1 by 4. This has taken more than 10 minutes because I need to explain that intensity concept. So definitely it will take more than 10 minutes. Now when I do this, what is the answer I get? So I will get 39 divided by 5.67. I am doing only so much. Okay, I'll retain the power over here. So which should be 6.87. I'll write this as 6.87 to the power of 4 divided 10 power minus 8 whole to the power of should be 10 power minus 2. Okay. Now here what I will do, I will now find out what is 1 by 4, right? Okay. So I will take the square root of, I have to take the 1/4 of the root. So what I will do is first for this value I will take square root. I get 2.62. Again I will take square root. See, 2 times square root I have taken for this. So I'll get 1.619 or 1.62. Okay. So therefore I will write this as a 1.62. 10 power minus 2 goes upwards, it becomes 10 square. So this should become 162 Kelvin, right? So answer is 162 Kelvin. Okay. Now let us move on to the next one. Ceres has a long rocky core covered with solid ice. The mean temperature is higher than your answer in A because radioactive nuclei in the center of the Ceres are decaying. So what's happening? You have, this is your planet Ceres. Okay, inside this Ceres there are some radioactive nuclei present over here. So they are decaying. What do you mean by decaying? They are giving out some amount of energy over here. Alpha, beta, gamma decay that we already learned, right? Outline how the energy from the radioactive decay reaches the surface. So what is happening over here? So as a result of it, so what's happening when the decay reaction occurs? The neutrons or maybe the alpha particles or beta particles, they start releasing, they start moving, and as a result of it, the kinetic energy now starts increasing. Kinetic energy starts increasing, and when kinetic energy starts increasing, what happens? The atmosphere present in the what you call Ceres, or maybe you can say the solids over here, will now start heating up. And as a result of this heating, what happens? The what does it say? How the energy from the radioactive decay starts increasing. So therefore, it gets heated up. When this gets heated up, now what is this here? So is it a gaseous planet? It's not a solid. It's not a gaseous planet. It's a solid planet. So it's already given. Rocky solid covered with solid ice. What does it do? Then the heat is being conducted. Okay, by ice. So now what does he extract from here? This is for 2 marks. Outline how the energy from the radioactive decay reaches the surface. That's your answer. Okay. So what exactly happens over here? it reaches to the surface because there is a thermal effect there. Why do we get thermal effect? Because kinetic energy increases as a result of the radioactive decay, and as a result of it you have a heating effect, and this heating effect is conducted by ice, so thereby it can melt the ice over here. Clear? Okay, now let me move on to the next question. See, we already finished 10 minutes, right? At low temperatures such as mean temperatures of Ceres, water undergoes a phase change directly from solid to gas. Okay, from solid to gas. What is happening over here? At low temperatures, mean temperature of Ceres, water undergoes a phase change directly from solid to gas. So there is no water being formed. Compare the molecular conditions of the solid phase and the gas phase at the same temperature. So what are the molecular conditions? Okay, so first one is gas. So what is the difference between the these two states? That's what is being shown over here. So molecular nature. So gases, what is so special about the gases? Gases will have low molecular interaction, right? Gases will have low molecular interactions than solids, because you need to compare between a gas and a solid. First point we have written is for 3 marks. I need to give at least 3 marks over here. Then in case of gases, what you can see, the molecules are farther apart, right? In case of liquids or solids, what can happen? The molecules are very nearby here over here, right? Because he is going to compare between these two, the only solids and this you have to say. So you can say gases, the intermolecular distances are too far, while as compared to solids, because in solids they are very nearby, okay, but in gases they are very far away, right? Then second point is that, then what is the next one? In gases, molecules in gases move freely, right? They are not bound by any bonds over there, they can start moving as compared to solids. Okay, everywhere you have to mention this, okay, because you are comparing between these two, you are given 3 conditions, so therefore everything is fine. Okay, so you will completely get full mark for it. Okay, now let me go for the next one. The maximum surface temperature of Ceres is minus 38 degrees Celsius. Okay, observation shows us significant quantities of water vapor are released from the surface of Ceres every second when temperature is at this maximum. This is a maximum temperature. Oh, calculate the mean kinetic energy of a molecule and mean kinetic molecule of water vapor at this particular temperature. So what should you do? So what is mean kinetic energy? Mean kinetic energy is given by the formula 3/2 kT. Very simple. So T, what is T? Minus 38. You have to convert this one into Kelvin. So let us write this one. 3/2 into what is K? 1.38 into 10 to the power of minus 23, the Boltzmann constant, multiplied by what is this? 273 minus 38. Okay, so when I do this, what do I get here? Let us find out. This should be 1.38 into 3 divided by 2. Okay, and this is 273 minus 38 star. How much is it? 273 minus 38. Close this. I get this as 486.45. 486.45. What is the unit over here? The unit here. Kinetic energy, joules over here, right? But I want this only in 2 decimal places. I can now say this should be nearly 490 joules. This should be your answer. Okay. Then did I miss anything? Oh, maybe miss something over here. 10 power minus 323 we missed. This is not 490. I'm sorry. This should be 486.45 into 10 power minus 23 joules, which should be equal to 490 into 10 power minus 23 joules. Make this correction. So it is 490 into 10 power minus 23 joules. Okay. Or significantly, if you write this for 1 mark, right? Okay. I can write like this: 4.9 into 10 to the power of minus 21 joules. Right. Next, the following data is available. Radius of Ceres is known, mass of Ceres is known. Show that the gravitational potential of the surface of Ceres is about so much. Quite easier. What is this now? G is equal to Gm divided by R square. Okay. What is G? 6.67 into 10 to the power of minus 11 multiplied by mass 9 into 10 to the power of 20 divided by R square. Because you are finding out the gravitational potential at the surface of Oh, we are finding out gravitational potential. Gravitational potential is given by capital V equal to Gm by R. Okay, and R, what is R here? R here is 4.7 into 10 to the power of 5. Okay, now let us find out what is this value. So let me take this 6.67 star 9 divided by 4.7 is equal to minus 12.77. So 12.77 into 10 to the power of 20 minus 11 is 9. 9 minus 5 is 4. 9 minus 5 is 4. Right? Okay, 10 power 4. But you know, gravitational potential is an attractive potential. So you should have a negative sign over here. Negative sign. So this should be negative over here, which should now be equal to minus 12.77 into 10 to the power of 4 joules per kg. Or, now what do we need here? I need to be of the order of this one. So which I can write this as minus 1.27 into 10 to the power of plus 5 joules per kg. Okay, minus 1.27 is nearly equal to minus 1 into 10 to the power of 5 joules per kg. Thus, we are able to solve this question also. Okay, anything else? Okay, that's it. Okay, let us see for more number of questions from tomorrow. Okay, thank you.